Square roots and real numbers. Our objectives are to evaluate expressions containing square roots, as well as classify numbers within the real number system. Why learn this? Square roots are used to find the side length of a square when you know the area of the square, like when covering a square plot with flower seeds. A square root is a number that is multiplied by itself to form a product. A perfect square is a number whose positive square root is a whole number. So if you look at the table below, 1 squared is 1, 2 squared is 4, 4 is a perfect square. 3 squared is 9, 9 is a perfect square. 16 is a perfect square. 25 is a perfect square. 36, 49, 64, 81, 100. I would make sure you add these to your notes. It's a nice reference to have. Let's look at finding square roots of perfect squares. So find each square root. Well, what's the square root of 49? So what times what gives you 49? 7 squared equals 49 because 7 times 7 is 49. So therefore the square root of 49 is 7. What about the square root of 36? So what times what gives you 36? Well, 6 squared gives you 36, so the square root of 36 is 6. Now, you have a negative sign sitting outside of this square root. Your negative can't be under the square root. You would have an unreal number. So, your negative kind of carries through. So, you take the square root of 36, which was 6, and then add in your negative. Let's look at classifying real numbers. So, you have natural numbers, whole numbers, integers, rational numbers, irrational numbers, and all of these are what we would classify as real numbers. When you get to Algebra 2, you'll talk about unreal numbers. Natural numbers are your counting numbers. Your 1, 2, 3, 4, 5, 6, all the way up. Your whole numbers are all of your natural numbers, only they added in 0. So your whole numbers start at 0, 1, 2, 3, 4, and keep going. But notice how the natural numbers, that circle in this Venn diagram, is inside of your whole numbers. That means all natural numbers are whole numbers. Likewise, all whole numbers are integers. But integers goes even further. So integers adds on the -1, -2, -3, -4. So integers are not just a negative number. Integers could be 0, 1, 2, 3, as well as your -1, -2, -27. Because an integer, every whole number is an integer. Every natural number is an integer. Every natural number is a whole number. Notice how the Venn diagram, the circles just keep getting bigger, but everything inside the integer circle is classified as an integer as well. Alright, now we have rational numbers. Rational numbers are numbers that you can make into a fraction. So, like 27 fourths, 0.3, -10 over 11, 4.5, 5/9. So you can make 0.3 repeating into a fraction of 1/3. 4.5, you have 4 1/2. Just because it has a negative sign doesn't make it an integer. An integer has to be either a whole number or like a -1, a -3. As soon as you're making it into like a fraction, so it's like 10 over 11. So 10/11ths isn't a whole number or a natural number. So therefore, it's a rational number, even though you have that negative sign in front of it. But once again, all whole numbers, all natural numbers, and all integers can be rational numbers, because can you make 1 into a fraction? Well, yeah, 1 over 1. How about -3? Well, yeah, -3 over 1. Let's look at the irrational numbers. Irrational numbers are like the square root of 17, or pi, like 3.1415, and it keeps going. These are where you have decimals that don't terminate. They just keep going and they don't repeat themselves. So they're irrational. Let's look at what we just said, but in words. So for those that need it in words, here we go. Natural numbers are the counting numbers, like 1, 2, 3, and they keep going. Your whole numbers are the natural numbers and 0. So 0, 1, 2, 3, and then they keep going. Integers are whole numbers and their opposites. So -3, -2, -1, 0, 1, 2, 3, and they keep going in both directions here. Rational numbers can be expressed in the form a over b, where a and b are both integers, and b can't be 0. So like 1/2, 7 over 1, 9/10. Those are all rational numbers. Now you have terminating decimals. Terminating decimals, think terminating. If you're terminating something, you're ending it. So they are rational numbers in decimal form that have a number of digits. So like 1.5, 2.75, and then it stops. So it's a finite number of digits. It ends. Your repeating decimals are also rational numbers. They're in decimal form, and they have a block of 1 or more digits that repeats continuously, like 1.33333333. That's what that little bar means. And then you have 0.66666666, and it keeps going forever. Or you can have it with two numbers that keep repeating. So like 0.141414, or 6.2777777. If it's repeating and it just keeps repeating the same number or same group of numbers, it's still a rational number. Now you have irrational numbers. Irrational numbers cannot be expressed as a fraction. They include square roots of whole numbers that are not perfect squares and non-terminating decimals that do not repeat. So the most common one is often like the square root of 2 or pi. The square root of 11 also comes up often. Let's practice classifying them. All right, so write all classifications that apply to each real number. So we have 8 over 9. Well, 8 over 9 is a rational number, and it's a repeating decimal, so it keeps repeating. Take a moment, pause the video, and try B and C. Now that you've had a moment to try B and C, let's try them together. Well, 18. 18 is a natural number, a whole number, an integer, a terminating decimal because it goes 18.0, so it stops, and a rational number because you can make it a fraction. All right, now we've got the square root of 20. Well, the square root of 20 is just simply irrational. It's not making any sense in the world. It's irrational. So we've got 4.472135. It just keeps changing its mind as to what numbers it wants. It's being irrational. So therefore, the square root of 20 is an irrational number. And well, that's that. So that ends our video, or our video lesson, I should say, on square roots and real numbers.